I'm Dániel Berényi. I am from the Wigner Research Center for Physics from the Hungarian Academy of Sciences. Now that's a pretty long title, but it means that I'm a physicist. And I'm a PhD student there. And this does not mean that I'm qualified to be here, because I'm usually writing number crunching simulations, high performance simulations in C++. Okay, so the rest part of the talk will be the justification why I'm here and what we learn from Haskell, or why Haskell. And I hope to introduce some concepts that would be interesting for the beginners, maybe not the most challenging for the experts, but I hope you will find it interesting. So for a small introduction, our institute is one of the largest research institutes in Hungary, and we are a member of many important international collaborations that you might encounter in the news. For example, we are members of the CERN LHC, where the Higgs boson was discovered. We are members in the gravitational wave searches, colleagues working there. It is the next Nobel Prize winning discovery, maybe. Colleagues were part of the Rosetta mission, landing a satellite on the comet last autumn, if you remember. And also there are guys working in the fusion experiments, so we may have a new clean energy source, so quite a lot of things. And all of these are related to physics. But physics is, not just about calculating equations on the paper, but also it has IT connections. We have the largest off-site compute infrastructure of CERN located at our institute at the top of the Buda Hills, because simply they couldn't afford to put another big cluster at the CERN campus because the power requirements were too high, so they chose to place it or construct it off-site somewhere, and the long-standing work of the Hungarian colleagues were rewarded by the opportunity to host a data center, a quite big data center, and we are really proud of that. And from my group, we are a small research laboratory called the Wigner GPU Lab. It means that we are working with graphical processing units made most of the time, providing a small GPU cluster for development of the colleagues who would like to experiment. We have all kinds of cards from different vendors to play with. We provide some developers assistance to all the guys who have questions. We are organizing the annual GPU day when we invite vendors and researchers from different fields to tell their experiences. We give some lectures, and even if at the end of the day we have some time, we really develop some simulations that actually do something. And when it turns out to be hard, we seek and evaluate new and emerging technologies, participate in the discussions and developments of the existing ones. We are members of the Kronos OpenCL advisory panel, so we are giving feedback on the APIs that you, at the end of the day, will be using to program the GPUs, and we keep annoying the C++ committee members why the language is not like something that is usable. Okay, so most importantly, we are trying to find the best language combination of all what is available outside that could support generic abstract mathematical constructs, because physics has really plenty of mathematics behind it, usually implicitly. And we try to formulate it into simulations that could run on clusters, GPUs, and whatnot, because there are many architectures out there. And also being portable, so you are not just tied to one architecture or one operation system. It should be generic, so you don't want to rewrite everything from scratch just because some researcher said, okay, I have to put in one more variable, and what happens then? It should be user-friendly, developer-friendly, and there is a long list that we couldn't go into detail. So most of the parts that are currently in use, usually in scientific environments, are written in C++. We mostly try to work with modern C++. I don't know if any of you follow the recent developments of C++. There are plenty of new features that are really good, and they keep coming. And there are good guys working very, very hard to incorporate more and more functional constructs into the language, motivated by, for example, Haskell. And while the progress is promising, it's a little bit slow, but we are also keeping an eye on Rust. How many of you guys heard about Rust language? Oh, great. Okay, so I don't need to introduce it, but we're also blinking at Haskell and F#, what could be used and learned from them, and how we can build simulations by that. Okay, so how Haskell comes into the picture. There is a good community, just look around. It's a really clean syntax compared to almost everything else out there. There is a good representation to sync in, and so on and so on. It's a good entry to functional programming. You have tons of resources on the internet. And most importantly, there are many interesting and useful abstractions that were developed or available via Haskell, put into there from category theory and other stuff, because extracting meaning from the mathematicians' articles are really hard. How many of you can read the category theory articles written in plain mathematics? Not too many. So you know what I mean. It's much easier to comprehend the Haskell code. Now, I would like to talk about trees for most of this talk. Trees are everywhere. Just think about the document object and layout models that are used everywhere, from the Word, the text document editors, and also on the web, and so on and so on, describing UI and also other stuff. If you are thinking about 3D modeling and geometry, there is constructive solid geometry of building different shapes by combining primitive ones with Boolean operations. And of course, there are binary search trees and space partitioning stuff. If you are working for the lambda cube on the BSP file format, probably you encountered the space partitioning stuff. If you browse in Google Maps, there are hierarchical data. So all of these, at the end, storing some things in tree structures. But for our purposes, the most important point are around the abstract syntax trees and things like that that describe computations, expressions in a tree-like manner. Okay. This will be a very really fast and hand-wavy introduction to the fixed point and the tree structures. So I apologize for the experts. I'm limited with time on that. The most important point is that first at the value level, we would like to have some recursion, and I'm going to use this example to motivate what will come after. So we define this fixed point function, this fix f, that will act as the factored out building block for general recursion, primitive recursion, and you see what it does is really a simple thing. It takes an argument of a f function and applies to itself. And if you write out, it could be repeated forever. Now let's write a factorial function with that by using a factorial proto that really does just one step in the recursion. So calculate one multiplication of the n number that it was given, if it is not 0. So there is one application here, and what it takes as an argument is itself, the recursive argument, and the number that to operate on. And of course, if we would just write this part, it would run for forever. So we need a condition to exit from it, and this will end the recursion when n decreases to 0. It is decremented here. Now, this is just one step in the recursion, and if we would like to make this really recursive and repeat for a larger number downwards until it hits 0, we can use this fixed point combinator that we wrote upwards, and we just fix the function, the prototype, and we are done with the wanted factorial function and use it and calculate whatever we need. Okay, so this was at value level. Now, one level up, we are going to do it at type level. The syntax is really similar. We now have a type constructor that applies itself one time, and what it takes is really just another type that could be fed into itself. You can see the similarities for compared to the value level. Now, we are going to use this to build trees by just giving one level, defining one level of the tree without recursion, but expecting one argument that will be itself, and then use this type level fixed point combinator to create the recursive type that we'll be using to represent the tree. So as before, we need a condition to exit at some point of the recursion, and in this small expression tree language that we would like to consider here, we have a constant integer node when there is no recursive position. R is missing from it, so it will mark the endpoint of the recursion, and all the others, now I have just addition and multiplication in this tree, are making the location of a binary branch that will continue until it was hitting somewhere at the very depth const branch. Okay, so we have this induction step and the exit condition. This is really cool, and we can fix this type and now use this expert type to create and store our tree. How we create such a tree? For example, we can take the constant node, the constant branch from the sum type, give it some integer, and then fix it, and we will have the fixed tree type, and we are fine. If you would like to build a one level deeper structure, for example, multiplication of two constants, we create the two numbers first. Just okay, I have a typo here. Sorry, in should be replaced by fix. Sorry, it was a very quick go. So after we constructed the two numbers, just as in the earlier example, we push it into the multiplication constructor and fix that again. And we can repeat this process and build up arbitrary trees that we would like. Now, the interesting part comes when we would like to do operations with these trees, and the most important ones are the bottom-up and top-down processes that are consuming, creating, or just traversing the tree from different directions. We need one helper for that. This is the inverse of the fix, where we reveal one level of the structure that we are considering, and we are really just looking more deeply into the structure, and we can access the underlying sum type. For example, we can have a pattern match on it and then do something with the internals. Okay, so without any detour to the algebraic background, these are called catamorphisms and anamorphisms that represent the bottom-up and top-down processing of the tree. And you can see that these are really the duals of each other, and I will be discussing them in depth. The main thing that you need to see here that we are supplying them the logic separately of the traversal, and this logic, what to do at each step, is called the algebra in the case of the catamorphism, and called coalgebra in the case of the anamorphism. If we take, for example, first the catamorphism, what it does, it is applying this inductive step logic, the algebra, for each stage in the tree by starting with the tree, applying this unfix to reveal one depth of the tree first, then step into it and apply itself to it, what is underneath, and repeat this, of course, until at the very end the recursion ends at the constant node, get back, and when it gets back, it applies this logic for the current location where it is standing, and resulting back the outcome of this logic upwards. Now, it can be a little bit more understandable if you take a look at the types that are involved. Our tree is the fixed functor that we have taken. When we apply unfix, we really just reveal the underlying structure, and then fmap on it. And if you take a look, once we fix what is the logic, the algebra, we just end up with a fix f to a signature. This means that inside the functor we replace fix f with a, and that is the outcome of fmap. And then the algebra will eat away the f from over the A, and A will be the result of the of one step of this application, and this is repeated again and again. Now, why it is a bottom-up traverse? Because first we always step into until we reach the constant part where this fmap does nothing because there is no inner type to apply to, and then gets back and applies the R repeatedly upwards. Now, take the dual. We reverse the arrows and reverse everything. Now, we start with a seed that is of type A, and our logic creates a functor from this A type. First, it applies to the coalgebra. So it creates one level of the structure, then step into it via the fmap and repeat the same process again. And once it is finished, it will just fix and wrap the type into the tree structure. If you take a look at the types, we start with the seed of A. We apply the construction, the inductive step once, so we get an FA. We step into it and apply the coalgebra. It changes the A to FA. Changes the A to fixed F. So now in the F we have fixed F, and by fixing it again, we hide the underlying structure and just get back the fixed F3 type. Okay, so it is a bottom-up traverse because we build the structure from the seed and going until we reach a constant node that we cannot step into further. Okay, so I'm going to give some small examples what these could be used for. All of these will be available after on the web page. I just didn't have time to send it already. So a really simple application is the pretty printer for our language. Now the logic that we are applying at each step is if we have a constant node, we just showing the integer value that we are storing at the constant node, and all the others will be just a concatenation of the sub-results and printing some nice parentheses. Always keep in mind that this algebra always receives evaluated subterms here. So this x and y would be just a list of characters, nothing of the functor structure is there beneath because it is already evaluated. And of course we can evaluate our expression tree and calculate all the additions and multiplications, and now everything will result in a simple integer. And really what we did is to factor out the recursion in these two cases, and we just had to write the logic once, logic for the different applications. Okay, so let's create an example for the anamorphisms. It's a little bit involved. Now we have extended a little bit our expression type. Now we have addition, multiplication, and power. And I will be using this small decision to restrict our recursion in some cases. So do recursion or do not do recursion in some stages. And this example, you will see the source code will start with a number, actually two numbers. We specify a base and take an integer and factor it into a sum that will be different powers of the base that we have given. So it's, for example, if you just think about the base of 2, it will expand the number into the binary form of power of 2s. I will show some sample output. Maybe it is easier to have it first. So if I start with a base of 2 and with a number of 31, I can break into sums of different powers of 2. I can take another base, for example, 4, and now I can break another number into powers of 4, a sum. So we start with one number and end up with an expression tree that I will be printing with the same showf that was used before, just a little bit expanded. And now the logic inside is built into this coalgebra that takes a pair, an integer, and this recursive decision. If the decision says do not recurse, I'm just writing out the value into the tree. If it is smaller than the base, I do not care about the decision because I don't want to break small numbers into, again, powers of the base. And now I'm just at the other two cases, decide whether it is a perfect power of the base. For example, if I just supplied 64 to the base of 2, it is a perfect power. I do not need to break it further because that's what I'm looking for. And in this case, I'm just putting it to the power node and disable the recursion both in the base and both in the exponent location. Otherwise, I really do a break into a sum and calculate what should be the power and the exponent and recurse into both of them. Okay, so this is somewhat artificial, but you can see the logic that what anamorphisms do. Now, the funny part is when we start with so the A type that was in both of the algebra and the coalgebra is itself a tree. So we are transforming trees into trees, and just the direction of the transformation is different in the two cases. For an easier example, we are doing a cost estimation on our tree with some logic. The tree is the same. We have addition, multiplication, and power. And we are adding one more information to this type, an integer that will represent somehow the computational cost of the level and everything below it. And we will be filling out this integer starting from below, from the constant nodes. Okay, our logic will be, of course, a catamorphism because we are starting from beneath, from the deepest parts. We say that whatever a constant node is in any leaf, it will cost us 1 to evaluate. If I have an addition, I say the cost of the addition is 1, and I'm adding to the cost of the childs that are below it. I say that multiplication has a cost of inherent cost of 2, and the power has an inherent cost of 10, and again, I'm just adding it to the cost of the childs that are below. And what happens is that if we start with a simple tree that has no cost information stored in it, it has a power, a multiplication, and an addition, and after I have run this catamorphism, it fills out the costs that I was expecting, and I can see that at the outermost I have 17 as a total cost of this tree. I will be talking a little bit why it is important to us to have such things. There is one more complicated example that I prepared. It is a simple lambda calculus evaluator. Now we need to expand a little bit on this tree construct again. We need to add the variable binding a name. It will be just a simple character that we can choose for it, and we will have abstraction and application. So this is where we introduce a new lambda, and this is when we apply an expression to another expression. Now we need to store some stuff during when we traversing the tree, and in this case we have this eval f that we are taking along. It contains the tree. It contains a stack of unbound expressions that were previously applied by an up node, and there is an environment that contains the already bound expressions that have a variable symbol and the tree that was bound to it. And we'll be using this fixed, fixed to store it. So the idea of the evaluation is the following. We first use an anamorphism and start from the root of the tree and take all of the up nodes and push the operands to the stack one by one. And when we met with an ups node, we take one operand from the stack and bind it to the symbol of the lambda expression. And we keep it repeating And when we hit a variable, we search for it in the environment and just replace it with the expression tree that we were storing in the environment. So it is really simple, and of course when we finished, we are starting with the catamorphism and really just evaluate all the things that we did. So the actual replacement is done in the anamorphism. Okay, I'm just showing some main points of the routine. You can take a look into that afterwards. So our coalgebra will take a look into the tree that it was given, and pattern matches the expression, the stack, and the environment that is stored in it. And in this case, we are seeing the ops node, and what it really does is take off the tree from the stack. Now it should be removed and passing towards the child nodes, and add it to the environment with the current symbol that we have in the ops node. So the deeper nodes will see the bound expression. In the opposite case, when we have an application, we push this node to the stack, and it will be used in the underlying nodes. The algebra that we use for evaluation is much more simpler. When we are adding and subtracting, we just really doing the operation, and when we should not encounter a variable, it should be all replaced, or if we really do it, there is an error in the tree. And when we meet with an ops, it should be an identity operation, and also for the up node, because it is already done in the anamorphism. And we really just partial apply this algebra and coalgebra with our recursion schemes, and we just compose the two, and first our tree will be preprocessed by this anamorphism, filling out all these locations and doing these substitutions, and then evaluated with the catamorphism. And we, in such way, can get this lambda calculus evaluator. Now this composition is actually and has a separate name. It is called the hylomorphism, and this all stuff is really working. If I'm taking a look out of it, and I can show you the actual source code. It will be available on the web page. It is not that much, and we can really build small examples here that, for example, create a two argument function and doing a subtraction on two values, and then we can really just evaluate the composition and see the result at the end. It is on the other screen, of course, and we got 42, and everyone is happy. Now, of course, if we have a simple lambda calculus, every functional programmer will ask, what happens if we take an infinite recursion? And here you can see that this expression 3 is the well-known y combinator that applies itself until infinity. And I can give it to this evaluator and see what happens. And once it finished linking, we can see that, yeah, it keeps running. And at some point we're running out of memory, and things will start to break loose. So what we did is really actually this what we did is really a simple lambda calculus evaluator and do what we expect. So if we really compose these two morphisms, we are losing determination guarantees and could write infinitely running programs. So how all this stuff is relevant to physics simulations, because it's, you know, it's just theory and computer programming and whatever. So there is a theorem, scientists are not good at programming. Okay, so it is a not so fortunate thing, but there's a justification because it is not their job to be. So they should be writing equations and dealing with symbolic stuff, and not to write, you know, number crunching program. And the corollary is that the field is full of inefficient code, because of course there are no good tools that could take symbolic equations and then create some really, really optimal code at the end that will be doing all the low-level stuff. Now, this problem is so serious that there was a review of the codes that are used at CERN for all the particle physics simulations, and it was turned out that they are using less than 1% of the hardware capabilities. And this is really a bad thing because the computers cost money, and if you say that you are just using 1% of it, nobody will give you more money to buy more hardware. Okay, so you need to start optimizing your code, and of course it is really hard because we are talking about hundreds of megabytes of source code, and it is difficult to look through and review it. And the other part of the story, that in some parts of the physics there are really codes that were written at Los Alamos and nobody touched it since because it works. Okay, so scientists need some domain-specific languages to express the algorithms and equations in their field. So there is a field jargon for every subfield of physics, and some specific language is needed for it. And of course, it means that we have some domain-specific language, we have trees. And just put here a simple equation from undergraduate physics. You can imagine that there are pages of implicit assumptions and types hidden in this notation that should be supported in such a domain-specific language. So this is a high-level task, a high-level expression that should be processed down in multiple steps until we get a really efficient numerical simulation, probably in C++. I'm just writing it because we think that the most efficient compilers are developed for C++, that as far as we see, and it should be running on clusters and GPUs and probably other hardware. So this is the task that we are investigating in multiple cases and multiple attempts. We have a prototype implementation that is targeting linear algebra only, and it is implemented, this specific embedded language and all the catamorphisms in C++, and it is working. It's an interesting study, but it still not solved the problem in all of this glory. So high efficiency is really obligatory because there is usually computation demand. So our algorithms and problems are compute limited and not memory limited. But we really, on the other hand, need the high-level formulation because some high-level optimizations cannot be carried out at the instruction level or low level or LLVM level or whatever you are using because you simply lost the context that you were doing some crazy mathematical operation that has a certain structure that you should exploit. It is completely lost when you are going down to the lower representations. So that's why multiple steps are needed. And if you ever encountered with numerical solvers, they have many wheels that you can fine-tune how it should work, what should it do when it is not converging, and all these crazy details. And some of it is inferable from the upward structure, the original formulation, and it should be automatically, fine-tuned or at least set to some good values. Just example, if you have a differential equation and choose some sort of discretization, this discretization will be influencing the structure of your matrix that you are getting, and you may choose a specific algorithm for this structure, and you don't need to choose it by hand. It could be chosen by a proper algorithm. Okay, so trees not just emerge by writing these language expressions. Even if there is a flat programming task, there could be induced tree because of the underlying hardware. For example, I'm talking about memory limits, all the caches, and hierarchical parallelism. Just take an example. The end user comes that give me a tool that can multiply matrices efficiently because I need to do it for tomorrow. Okay, so the programmer asks, okay, no problem, let's use a GPU library. How big are your matrices? 10 to the 8. Calculating. How big is 10 to the 8? It is really big. It will not fit into anything. Well, is it storing floats? No, complex doubles. Okay, so this is a typical scenario. So let's take a look into it. Matrix multiplication is a flat thing. We just have two outer loops on the result and one internal loop that calculates a dot product of the one row and one column of the respective matrices. It's not that bad, it's just a few lines of code in whatever language. Now the problem is, it was a flat thing, but above n equals 1, so we are talking about n by n matrices. Around n equals 4, you run out of the vector registers of whatever architecture you are using. Now, it's important you take use of the registers and push as many data of the matrix as you can into them, because it is really the fastest way to do operations, and accessing anything outside of registers costs time. Now, around n equals 16 and 64, you run out of cache or local memory or whatever it is called on your architecture. It is at most, say, a few kilobytes. This is the fastest memory that is nearer to the registers. And on GPUs, you are going to run out of workgroup threads where the synchronization is possible and cheap. It is around 256. Next step, at n equals 16,000, you run out of the maximum single allocation on GPU. You need to separate your matrix into different allocations because there is an addressing limit and other limitations in the device or the implementation. A factor of 4 later, you simply run out of the maximum thread count because the thread index is limited to some bits. And later you run out simply of the total video memory, and you may try to use multiple GPUs, but you will going to run into multiple issues with that. And above n equals 100,000, you run out of your RAM, the random access memory, or whatever you are using on your host. You need to stream to the disk or SSD, or you simply try to use distributed parallelism. And it means that around 10 to the 6, you simply give up. And the user comes back that it turned out that he really needs 10 to the 12 because of some technicality and mathematics and whatever. So this is really a case that is usually happening. Implementing such things properly is really too slow because the underlying theory changes much more faster. So something should be done to it and automate as much of the problem and the process as it is possible, and taking use of all of this. So of course the underlying stuff is that you need to partition your flat algorithm, your flat data, into multiple levels repeatedly. And this, of course, induces a hierarchy. So you started with, I love to use power types, that your A, the underlying type, that was a complex double, for example, raised to some product, where n is the size of the matrix. And it will become a nested power type, where the different levels show the different sizes at each level. And of course, their product should match the same thing. Now, voila, we have trees again, and now we have a hierarchical data that we should work with. Now, if we were lucky if we had a flat type at the beginning, because if there is an inherent structure in the data, and you have a different hierarchy because of the hardware, you need to match the two, and you are ending up with crazy mathematics and divisibility problems and all that you can imagine, and start padding, and things go crazy. And memory type and other annotations may be placed in this tree that is now expressing just the hierarchy structure that you would like to use for your data type. It is, of course, and then you can use traversals to drive the placement of where one block should go into the different memories, and you can decide it by cost estimation, just the same things that are showed before. Now, usually, if you open up the literature and you look for a certain numerical algorithm, you're going to find imperative and procedural language-based pseudocodes. Now, this is a bad thing, again, because if you really would like to use functional programming and things, you need to reformulate everything, and sometimes it is not that trivial to really transform the code from the article. And reformulating them using these recursion schemes could be an interesting study, and we are really looking into that because it could reduce code bloat. You can reuse much more patterns in multiple cases. It will improve maintainability and maybe even making optimizations easier. We looked into some ordinary differential equation solvers, and it turned out that they could be abstracted by double-nested mutual recursion, for example, and it really simplified the implementation. But of course, you're not going to find it on the internet that simply how to do that. Now, there is a complete zoo of all these recursion schemes, you probably encountered it earlier. These are always, generalizing each of them. We just discussed the catamorphisms and anamorphisms, but you can generalize it further, and they are good for even more tasks, and you can recognize and use them in different scenarios, and we hope that they could be the main driving force to deal with all these three structures, do all the annotation, optimizing replacements, do the final code generation, and provide all the details that we would like to use, and we can then give all this to the scientists to work with. So this was basically what I would like to show to you. We are seeking for feedback, and if you have any nice articles or references on this subject, it would be very welcome, because it is really a hard task to look all of these, and dig up the literature is really time-consuming stuff. And if you are interested, here are some links that may be of interest, and there are further examples and further stuff. And I'm just saying thank you for your attention, and I'm really expressing my special thanks to Gabor Lehel, who really taught me all this Haskell stuff and introduced me to the subject. Thank you very much.
You are using Haskell to generate stuff, but not to do computations.
So the question was whether we are using Haskell. At this very point, we are just learning the abstractions from Haskell, and until this days, I would say that we are just re-implementing them in C++. It really works, and it is surprising. And now we are thinking about really transferring and migrating some parts of the C++ trickery back to Haskell, and then use it for just code generation and generating probably C++ code, some form of wrapped C++ where we have or some other abstractions that are really taking care of the memory management and other hard details that we would not interested in the syntax, because there's even further details that just could be wrapped and used as a building block, and we can use the code generator to generate code for these wrapped constructs and use them for whatever. And then we will separately compile the C++ code that will orchestrate the GPU and CPU and the memory management.
Mm-hmm. Any other questions? Have you checked the Haskell solutions for GPU programming, like Accelerate
yes.
or Obsidian?
Up to some degree. We've seen that the most developed ones are for CUDA usually, because it was the easiest to use. We have one big problem with CUDA. It is the vendor locking, that you are really then left to the choices of the vendor when a new architecture comes out, how good will be it for your certain tasks. And we are really after portable technologies, and when we checked last time the OpenCL version of these libraries, they were not that developing that fast. So we have issues with that. And on the other hand, when a couple of new APIs are coming out or under work nowadays for managing GPUs, and they will have C++ bindings, and then they should be taken account and wrapped inside these constructs up to some point. And so we would really love to see Haskell wrappers of them, but I don't know what the stage of.
Do you plan to build your own framework, or do you pick one as a base?
Well, it certainly needs some more research before we are making a decision. We are now at the point of collecting what is available, what algorithms should be used, and which part of them we recognize in our problems. So it is usually really a pen and pencil problem that we need to consider what is our physical problem, what is the numerical solver for that, and then recognize how we can express this solver algorithm inside some language or domain-specific language or whatever. So it is a non-trivial hierarchical task.
How much time do you plan for this research?
Okay, so it will be done when it will be done. Okay, so it is. We are really, of course, we are developing codes that should work in a certain fixed amount of time, and what resources we have beside that, we are pushing it into the research of this direction. But I'm writing usually plain C++ code for one day, and then spend another day try to rewrite it or try to reformulate it, or just throw everything to the scratch and start with a new abstraction and use some more information that I've gained in the last times.
One more question. When you are running a parallel computation on the graphic cards, can you combine graphic cards from different vendors, or do you always have to take the same vendor or even the same type of card?
Okay, so the question was whether we can combine different vendors' cards. In theory it is possible, but sysadmins hate it, because you will run into issues with the drivers and everything that you can imagine. So the safe bet is to always use one vendor's card, and preferably even the same architecture and same brand, same type of the cards, because no guarantees that it will work. In theory it is possible because some APIs could handle this, but the implementations are not always conforming, and there is always one bug that prevents you from doing it. Yep.
Wait, the thing you did with the calculations related to the choosing of what level of optimization to perform based on these kinds of information. Things like that isn't specific to scientific calculations. There's a lot of literature and practice in database algorithms specific to optimizing large queries, and you should look into that in order to derive some existing literature and practice and knowledge about how to automatically perform optimizations of some size.
Yeah, so the remark was on the similarities of databases and database research, and we really definitely would like to look into it, but we didn't have the resources and the references to look into that. So if you have some articles, please send it to me, and I will be really glad for that.
Okay, so no other questions, then thank you.
Thank you.
One last question. Is this open source? Any research what you done?
At some point we plan to make it open source. I think it again depends on the decision of my bosses, but at this point it is really just playing around, and we can of course open source it, but when you look into it you will just see a mess. So it is another question for a later time. Okay, thank you.